Hey there, everybody. It's Mr. Sheeline. Going to wait for this to kind of load up here. This is going to be the video lecture for Unit 3.1 notes. There it is. Forces, free body diagrams, and Newton's first law. So this is going to be a little quicker than usual because, again, this, like I mentioned in class, this is, not so much busy material. It's just not as much, there's not as many calculations to make here. It's much more conceptual. Okay, so let's just get straight to it. So free body diagrams. So free body diagrams, these are more or less representations, pictures that show all the forces acting on an object. All these different we're going to use vectors to represent the forces affecting different objects. And so typically, though there can be more than four on a free body diagram, typically free body diagrams express four types of forces acting on a particular object. There's the friction force, and there are different types of friction forces, which we'll get into when we get to friction. But friction force, applied force, I also will call this the action force, and the gravitational force, just gravity. Normal force as well. So, and here they are with all of their specific symbols, how we denote them, and what you should expect when we are writing these down on these examples. And so and there's a picture here in your notes that's a pretty good example. They obviously just kind of show it differently than I do, with different symbols as well, but that's fine. Okay, so here is an example of how you would draw a free body diagram for a book sitting on a table. So this is what it would be. So if this right here, let's see. Of course, I don't have my little pen here. So here, give me a second to get the pen, and I'm going to pause it, and we'll come right back as soon as I got that pen. There it is. I actually don't have to pause it. So let's take a look at this again. So the little gray box there, that's going to be your book. Okay. Come on. You can do it. So yeah, this guy right here, this is our book. Okay. And this book is being affected by both the normal force and the gravitational force. So it's just, if it's sitting on it, just chilling out on a table right here. So here's our table. Okay. You have the normal force that is pushing upwards, and then the gravitational force pushing downwards, or pulling downwards, I should say. So exactly what is the normal force? Well, just real quick, the normal force is more or less just, it's the opposing force to gravity. Think of it this way. If you didn't have a normal force, if we didn't have a normal force pushing, like say a table pushing up against the book, then for the most part, this book would be moving through the table. Because if you delete this, if you get rid of the normal force, get rid of that, and all you have is a gravitational force, yet you still have matter that is in between this object and its trajectory, its motion, that means it's going through something. That means that there is nothing to stop it. So think of it in this way when it comes to the normal force. The normal force is the force of the equal and opposite force that another thing will exert on something like this book that's sitting on top of it. Okay. Now, but we show the normal force in reference to the gravitational force. Okay. They oppose one another. Okay. So let's take a look at here. So check your understanding. Number one, a monkey hangs by its tail on a tree branch. So let's try to just draw the free body diagram representing all the forces on the monkey. So pause it here, and then come on back after you've drawn your free body diagram. Come on back and see what I made. Okay. So what you should have seen, or what you should have made, sorry. So what you should have made is, and this is the great thing again about physics, is that you can draw whatever you want, and I encourage you to draw because it'll help you immensely. Now, the only thing I will say is that you got to be careful sometimes of what you're drawing here. So if you do draw a monkey here, and you decide to draw all the work, so you're going to draw the, and I know this is going to look like a bear, mouse, monkey thing, but if you draw, a monkey here, God bless, that is yikes. But if you draw a monkey here, that's a sad tail. That's not what a monkey tail looks like. we're going to just give them that kind of tail. So if you give the monkey, draw him like this, right? Which is fine. The only problem is that it can be difficult to really represent accurately all of the different forces. So even in questions like this is how I draw. I'll be drawing, free body diagrams. Everything for the most part is going to be represented by like a box or a circle. And typically they're going to be boxes, just because boxes, it's much easier to kind of make directional or to show directional vectors. I guess that's a little redundant, but to show vectors kind of on two different planes, on the X and Y planes, it can just help, visualizing. So a monkey hangs by its tail on a tree branch. So more or less, so if this is our monkey, if the box is our monkey, and this is the tree branch. Now, it doesn't really explain exactly how it is grabbing to, this tree branch, but for the most part, we can say this. So, and actually, I'm going to draw that a different color. So, or actually, well, that's the tail of the monkey. So we've got a couple things going on here. So we've got a gravity. So we've got our force of gravity here. Okay. We also have a normal force. And we're just going to focus on the monkey, by the way. We have a normal force, but I don't think actually I mentioned this kind of force. So that maybe there's actually 5. Well, maybe I'll change that. So there's 5 different forces. So it will be a normal force, but the difference is we're not going to call it the normal force. Hopefully you're maybe thinking of this. Think of like ropes. What is it that you have when you hold a rope tight? What is that called? Hopefully you said it in your head. It's tension. So the normal force here is actually going to be the tension force. And the tension force is going to be through the monkey's tail here. Now, I'm going to draw this just a little taller than this guy down, than our gravitational force down there, just so you can see it. But it's going to be the normal force. So realistically speaking, so the tension force in this case is going to be more or less our normal force. So this is what we should be seeing as far as our monkey hanging on a branch free body diagram should look like. So again, our tension force here is more or less our normal force. Okay. Now you may be asking, well, Mr. Sheeline, what about the branch here? Yeah, yes, the branch is the branch. If we just looked at the branch, there is a force going this way, due to gravity, but there is also a normal force being pushed up at the same time, just not at this location, but it'd be closer to like the trunk of the tree. Okay, but we just want to focus in on the monkey. That's what we wanted to focus in on. But that's what we should have here. Okay, check your understanding number 2. Okay, so now the monkey hangs by both hands from 2 vines. Each of the monkey's arms are at a 45 degree angle from the vertical. Draw a free body diagram representing all forces on the monkey. So pause the video here, take a whack at it yourself, and then play again to see the answer. Okay, so the monkey has now moved on from his boring old branch to now there is, at a spot on the branch, now we've got 2 vines. Okay, and the vines just happen to be somewhat like this. So they said about 45 degree angle, give or take. Okay. Or the arms are at a 45 degree angle. So not the vines, but the arms are at a 45 degree angle. So maybe let's just start with the monkey here. So here is an arm, here's another arm, grabbing onto the vines. We're going to say the vines are going to come down to right here. That's going to be the 45 degrees, give or take. Doesn't have to be perfect. Okay. So here's our monkey. Here the monkey is holding on to the vines on this tree branch. Okay. So where are the forces? Well, for the most part, it really hasn't changed. So we've got a gravitational force that's still pulling us down. However, we do not have one going straight up from the gravitational force. The monkey is suspending itself with its arms pretty much 45 degrees is really supposed to just mean like it's an equal balance of forces here in the split second. So we should also know that there is a force going this way and a force going this way in relationship to the monkey. And again, these are, for the most part, our normal forces, but more specifically, this is our tension force. Okay, the monkey's arms are going to act as a tension force. Now, realistically speaking, normally we are not going to, I'm not going to give you questions where like this and then have you solve for it. All of the pieces are going to be provided to you to solve if you were having to solve like how much, tension forces in both arm, which we will be getting into. The only problem is like we don't really talk about the angle in which the vines are sitting. So for all we know, they could be, perfectly, vertically straight, or they could be bent, and that changes things. It changes because maybe what you're thinking here, well, Mr. Sheeline, isn't there a force being exerted on these vines? And there are. The only difference is that there is a gravitational force being pulled down on the vine, and then there would be another applied force being pulled this way. But then our normal force would be this way, but it also have a tension force of this way. So it's a little bit more complicated than what we're getting into, for right now. So again, just focusing on the monkey, and we're just going to say in this case the vines are perfectly vertical. They're perfectly vertical vines, and for the most part, this is what the free body diagram would look like with this monkey. Okay. So let's keep on trucking to number 3. So the normal force is always equal to the component of weight perpendicular to its surface. Wow, that's a really weird way of just saying that force of gravity, or the normal force, is just perpendicular to the surface something's sitting on. But the question being, is the block moving? So think about this for a hot second. Really, really think about it, because I know you can answer it. I know this seems like a difficult question, but it's actually a pretty easy one. What do you think? Is this moving, or is it not moving? Pause the video here, and then after you think you have it, come back and play. Okay, so the normal force is always equal to the component of weight perpendicular to its surface. Another way of saying that weird sentence is saying that the normal force is perfectly perpendicular from the surface it's sitting on. So meaning, nope, not the eraser. So meaning that the normal force is perpendicular to this ramp. Okay. So you notice that the ramp here is at an angle, and the normal force is perpendicular to the angle that this is sitting at. And then you've got gravity down here that's kind of looking like it's doing its own thing, but really it's not. It's doing exactly what it's supposed to. It's going straight down, straight vertical. So looking at this, we do have enough information to know if it's moving or not. Now, I'll just say that this sort of kind of is a trick question. Let me ask you, did we have an arrow this way with this? And was it ever mentioned up here? No. So what I'm just listing, what I'm saying here, they do not list in the question that there is friction. And sure, they don't mention that it isn't friction, or that it is frictionless. But there's no mention of friction here. There is nothing in our free body diagram that is showing friction. So if we just have these two, if we just have our normal force and our gravitational force, and we know that our gravitational force is typically on level surfaces, is in this direction, but we have a slight difference now that the normal force isn't perfectly perfectly equal or opposite direction to our gravitational force. That means that we are moving a little bit in this direction. Okay, we are moving a little bit, not terribly fast, but there is some acceleration here. Okay, so to recap real quick, if you didn't catch it, so because friction was not mentioned, and we just have the normal force and the gravitational force. Gravitational force here is at an angle. It's at an angle that would imply our box to move here. because it's not perfectly, our force due to gravity is not perfectly in line with our normal force. Because if it was, we would imagine that it wouldn't move. Just like the laptop that I'm using right now is sitting on this table. I wouldn't expect it to move because it's not at an angle. It's perfectly flat on my table. Okay. Gravity is moving in the same direction as my normal force. But in this case, because the force due to gravity is still pulling down, normal force is at an angle, that means that it's going to slide. Now, if it mentioned friction, and there will be questions like this throughout this unit. If it did mention friction up here, if it mentioned friction up there, or had the vector here, if it had the vector here like this, in this case we would say it's not moving. Okay. If we saw the friction force labeled here, we'd say it's not moving, because what that tells us then is that whatever movement is, that the box is trying to move in this direction, well, it's being stopped by this guy. Okay. So sort of kind of a trick question, but not really in its own kind of right. Okay. So let's start again to Newton's first law. So Newton, for the most part, during an extended period of isolation, because way back in the day, Newton was, for the most part, quarantined at home, similar to us. Oh, that's kind of weird. Yeah, more or less due to a pandemic. That's not a joke here. Due to a pandemic, he was more or less kept up in his home. During that time of him being held up in his home, the dude was able to produce literally make the math calculus, but he also was able to determine a number of things, and one of those things happened to be his 3 laws of motion. So we're going to lay out the 3 laws, but we're just going to focus in on the first one. So here are the 3 laws. So the first law is if the net force acting on an object is 0, then an object maintains its state of rest or constant velocity. We're going to break that down, okay? Then number 2, the second law, an object accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the object's mass. So what that is, we'll get into that later on. That is, force is equal to mass times acceleration. That's pretty much what the second law describes there. And then the third law, for every action force, there is a simultaneous reaction force equal in magnitude but opposite in direction. Again, we'll get to those 2 later on. We're going to focus in for right now on the first law. But no matter what, when we are describing what's happening, when we are measuring how much force is being applied in a particular space, particular thing, we use Newton's, labeled N, as a unit of force. And for the most part, Newton's is a derived unit, meaning that we have to use other, basic units in order to make it up and to measure it. And 1 Newton is equal to 1 kilogram times meters divided by seconds squared. Or in other words, that's mass times acceleration. Okay. Well, I just noticed a little, it underlined my exponent in the 2 there, all the way up to the 2. That's kind of strange. Anyway, so Newton's first law of motion, a body in motion tends to stay in motion at a constant velocity, and a body at rest tends to stay at rest unless acted upon by a net external force. And this we should have heard before somewhere, whether it is a pharmaceutical, either from a pharmaceutical commercial, or from school, or from anywhere. What that's describing is inertia. And so we'll call it the law of inertia. If the net force acting on an object is 0, the object maintains its state of rest or constant velocity, which is pretty much the same thing we've said now here for the 3rd time in a row. Now, what is inertia? Well, inertia is the ability of a body to resist acceleration by a net force. Okay, so think of something in space. So if we were out in space floating around, and let's say we're perfectly still, and you're like a foot away from me, okay? If I give you a push, you're going to start moving at whatever the amount of force I put onto you. You're going to be moving at that velocity forever. You didn't hear me wrong, forever. If we were up in space, you would not stop until something stopped you. So if an asteroid hit you, okay, that would stop you. A number of different things, moving at a decent rate, you would need something, either an opposing force to stop you, or, opposing in the idea that it's going the opposite direction that you were moving. Or you need to be lucky enough to find some kind of rope somewhere to grab onto. Is the idea. You'd literally go on forever. So let's apply that to Earth. So remember, in two-dimensional motion, we talked about how, like, if we shoot a cannon, when we resist, or when we ignore, when we ignore air resistance, and wrong example here, not the cliff ones. So remember, on the cliff ones, like when we would shoot like a cannonball or something, or it doesn't even have to be an angle. If we shot it this way, our horizontal velocity doesn't change. What does change is our vertical velocity, and our vertical velocity does. And it's because that the acceleration due to gravity pulls us to the ground, and then we hit the ground, and then the ground acts as a friction force then against our forward motion. That's what stops us. But if we didn't have gravity, if you don't touch anything, if you were to be launched and you don't touch anything, you would continue at that pace. And again, if you ignore air resistance as well, you would continue at that pace forever until you hit something or something hits you. Okay, so that's inertia. And then to cause acceleration, the net force acting on an object cannot be zero. Okay, and that's just a fancy way of pretty much saying that it implies two things. This is the first thing. It implies that acceleration, there's only acceleration if there's an outside force applying to something, and it also just means that if you don't have acceleration, that means that at that moment you don't have a net force. So the net force acting at an object cannot be zero. So it's just to say that in order to change your force, a net zero force, you have to give it acceleration. Okay. Now, the first law is counterintuitive because, and this is something I kind of mentioned when we were going through the projectile motion stuff, is that people to this day still believe that a force is required to keep an object moving. And that's not true. Once you provide that initial force, something will keep going. Now, if you're pushing, an object across a floor per se, yeah, you have to continually add a force throughout that whole time because you're opposing a friction force. You're trying to overcome that force that's trying to, hold that object back. So you have to continue. But again, if we didn't have gravity and if there was no friction on that object, you give it one little tap and it'll start going. Okay, relative to its mass. Okay. So even Aristotle firmly believed the idea that you have to continually add a force onto something, but so there you go. So now we know this, or if we did know this, you were slightly smarter than Aristotle in this very particular idea. Which, is it saying a whole lot? That could be. There's a lot of things that today that a lot of people didn't know throughout history, and even some of the greatest scientists, knew or didn't know. Sorry. Okay, so the number of implications, some of these I've already mentioned. So an external force is required to change the velocity of an object. Yeah, so again, that's just going off the idea that if you have a friction force opposing the motion of an object, you have to continually add force to it in order to keep that object in motion. But if there is no friction force, you don't have to continually apply a force to it. It'll just keep going. For an object to change its velocity, including changing from an initial velocity of zero, the net force must be greater than zero in one direction. So it just means that you have to overcome friction in order to get something moving, and you just need initial force to get something going. That's pretty much it. So, and then objects at rest remain at rest unless acted upon by an external net force that's greater than zero. Again, we've already covered this. and the moving objects continue to move in a straight line at a constant speed unless acted upon by a net external force. Again, mention that too. That's you floating in space, and the only thing stopping you from continually to flow forever is if something hits you or you're able to grab onto some mystery rope somewhere. Okay. Okay, so where do we see things that have zero net force? Well, a good example was that book. That is the book resting on the table. So the force. So here you've got the force of the the normal force of the table pushing back on the book. That is going to be exactly equal to gravity, the amount of gravity pulling the book down. Okay. So when we draw it here, now notice I know that this guy, my force of gravity is its vector is a little bigger. That's not on purpose. That's on accident. So if you didn't notice that, imagine you just ignore what I said there and just keep doing what you're doing. But for the most part, the normal force is going to be equal to the gravitational force. So in this case, we can say that the normal force is equal to the gravitational force. Thus, our net force is zero. Or you could say that the quantity of your net force, if your net force is a positive direction, let's say let's say that the normal force, or it'd be like the normal force minus the gravitational force. Well, if let's say the normal force is 8 newtons, and then or actually plus, sorry, it'll be plus. If up is our positive direction, well then of course the negative direction is going to be down, and it'd be like 8 newtons plus a negative 8 newtons, which is going to give us a net force of 0. Okay. So what does that mean? Oh yeah, remember we're using vectors, so because it's a vector, we're using vectors. Direction matters, and when direction matters, it'll change our values here. Okay. So where can we apply Newton's first law? Well, we can apply it here with a car slowing down. So when a car slows down, or just using a car in general, as you guys have already learned or are learning right now in driver's ed, depending on the student, or even something you should have known even before taking driver's ed, is that you have to wear a seatbelt, not only just because it's law, but you should wear a seatbelt while you're driving, because a seatbelt will save your life. Why does it save your life? Well, remember, we're talking about the law of inertia here. A body will tend to stay in motion unless acted upon by an external force. So if you're speeding at 60 miles an hour and the car, not you, the car hits some sort of wall, you will continue to move at 60 miles an hour. The car will continue to move. The car will stop, but you will continue to move at whatever the previous velocity was that the car was traveling at. Okay, and that's what we saw in that little demo, that horizontal, that ballistics cart demo. That's what we saw there. It's Newton's first law. The ball is going to move at the same rate as the cart, even if it's shot up, into the air. It'll maintain that horizontal velocity. So what do we use in order to kind of break, or not to break Newton's first law, but to prepare ourselves, knowing that it's there? Well, we have, breakable windshields, so that you don't explode when you hit the windshield. For one, it slows you down a little bit. 2, there are airbags that will decrease the amount of energy and the velocity that you are traveling at. And then the third one, is the biggest one, is your seatbelt. Your seatbelt is going to prevent you. It's going to lock you and make you part of the car for the most part, and keep you in the car. So you'll still travel at a decent rate. And it's not to say that all of a sudden it's magical, it's some magic where you're not going to get hurt. You'll still get hurt, wearing a seatbelt. You'll get rug burn, really nasty rug burn. Airbags are gonna bust you up a little bit. But I'll tell you this, having some scabs on your face and on your stomach and some bruises is way better than more or less dying. Okay, so I don't know, and it's not, and I don't know that you do what you want in a way, though I do support that idea. It is the law, though, whether you agree with it or not. It's a law to wear a seatbelt. But this is why. It's because inertia. Because again, if a car is moving at 60 miles an hour, you are moving at 60 miles an hour. And if the car suddenly goes to 0 miles an hour, you don't magically go to 0 miles an hour without a seatbelt. You're going to continue with that 60 miles an hour, pretty close to it, until your face hits the pavement. And then you'll start slowing down. Okay, so number 4, check your understand number 4. So real quick, and you exert a force of 45 newtons up on your backpack, causing it to move upwards with a constant velocity. Determine the force of gravity on the pack. So think about that for a second. Pause the video, see if you can figure it out, and then come back, and I'll solve it along with you, or at least provide you the answer. See how close you were. Okay, so let's just draw a free body diagram. So you're picking up your backpack. Well, first let's just say you got your backpack here, and it's being pulled down by gravity. Or actually, that's what we're solving for. But it's going to be affected by gravity here. But it's also being applied by your action force, your applied force here, and your applied force is going to be 45 newtons. So we have to ask, what's the force of gravity on the backpack? Well, if the backpack, and this is something that's kind of tricky about, this is what's tricky about the forces in trying to determine how much goes one way and one goes another. So you have the force of 45 newtons to pick it up. Now, there's no indication that there's any kind of change in velocity here. So because there's no change in velocity, there's constant velocity. Because we have constant velocity, that must mean then the force that's needed to pick this thing up is equal to the gravitational force. So that must mean that our gravitational force is 45 newtons. So I know that must seem weird, especially since we just talked about how a book sitting on a table will have what's the word? A book sitting on a table is going to have an equal net force, gravitational force as the normal force. But remember, this is not the normal force we're talking about. It's an applied force. And not only is it an applied force, I lost my train of thought there. It's not the normal force, it's an applied force. Now, let's say in this question, to maybe kind of clear it up, let's say in this question it mentions that when you pick up your backpack with at such a rate that it flies over your head, and you almost lose your grip on it. Now, if it were to be like that, as if it accelerated past the acceleration due to gravity, then you'd be talking about having a lesser gravitational force than an applied force. But again, because it says here at a constant velocity, okay, it's moving upwards at a constant velocity, there's no acceleration in the upwards direction. And because there's no change in velocity, that just must mean that we're using a consistent amount of force to pick it up. Okay. Now, again, it's tricky. This is tricky stuff, but it's not that it's impossible. So again, key point being constant velocity. Because it's being picked up at a constant velocity, that means that the whole time we are applying a 45 newtons, and gravity's pulling it down by 45 newtons as well. Okay, and I believe this is the last one. Yes. So a heavy block hangs from a string attached to a rod. An identical string hangs down from the bottom of the block. Which string breaks? Okay, out of these two options. So when the lower string is pulled with a slowly increasing force, or when a slow string is pulled with a quick jerk. So pause it here. Try to answer this on your own, then hit play and see what the answer is. Okay, so what we should know here is that the lower string that's being pulled slowly, this is the string that will not break. Okay, it won't break. So we'll put a green here. We'll circle this guy in green to say, yay, you won't break. But of course, that must mean then, ooh, the lower string with a quick jerk, that will break. Now, why does it break? We'll simply put, I mean, for the most part, we can imagine this because I'm sure we've done this before. If you've got a heavy block here and it's being pulled down, okay, and from a string attached to a rod. Now, it doesn't really specify how it's being held up, but let's just say it's held up like this, okay? So, and then we've got a tension force moving back up against it. So, and then an identical string hangs down from the bottom of the block, which string breaks. So an identical string hangs down from the bottom of the block. I think I'm missing something here. Here, hold on one second. So, okay, I figured it out. So I read these wrong. So the question is asking, okay, you've got a block here, and then you've got this identical string. So when you pull on the lower string slowly, which string breaks? Is it going to be? Maybe I'll draw the higher one blue, and then the lower one will be green. So which one breaks in this first scenario? And hopefully we would understand that in this first scenario, it's going to be blue. It's going to be the upper string. Okay. Now, why does that? Because you're applying a greater amount of force in this direction on this heavy object that's going to at some point break this guy up here. Okay. Now, that we can just think of in our heads for the most part and not too difficult. Okay, so when the lower string is pulled with a quick jerk, well, in that case, our lower string would break. So why would our lower string break? Well, more or less because of inertia. So because this guy has already been sitting in a spot and you have gravity pulling it down at this rate, and then you got the tension force that's the normal force that's being applied here in the opposite direction at the same magnitude. Well, if you quickly pull on it and you add a little bit to the you add a little bit of force to it, for the most part, your lower string is going to break, specifically because the tension force between your hand and the string, it's going to how to explain it. There's a lot of inertia that's going to resist your acceleration, since this guy is pretty much set and ready to go where it's at. And the force just won't reach up here. It's hard to describe outside of that. Just think of it in this way, because you've probably experienced it before. Is that when you yank on it, when you give a good tug on it, and inertia. All you need to know is that the inertia of this guy up here is going to prevent the force from traveling upwards to this string right here. Okay. All right, and that's the note. So not as long as usual, but still a decent amount of time. So if you still have any questions for me, make sure you ask, and I'll see you in the next one. Thanks, guys.